Hvala za tole predstavitev. Marko me je malo povišal. Magister sem, nisem doktor. Nič hudega. Vse v obstalem času, bom rekel. Torej, tale članek je bil napisan v angleščini, tako da bom nadaljeval v tem jeziku. First of all, good morning to everyone. The purpose of this study, or the topic of this study, is the behavior of pipe roof. We've been doing this researches at our faculty for a while now, and within these activities we analyzed different existing design methods. We analyzed case histories, and of course we also did a number of numeric analysis. And within this analysis, we also did a rather extensive parametric study in order to understand the concept, the behavior of the system of pipe roof. So since some of you in the audience perhaps aren't familiar with the concept of pipe roof, let me just make a brief introduction, what is it all about. First of all, worldwide there are different terminologies using this concept. In this part of Europe, pipe roof is probably the most common term, but worldwide you can encounter terms like umbrella, arch, shield, canopy also. But all these terms essentially stand for the same thing, and this system is essentially pre-support system, which typically consists of pipes which are installed into the ground almost horizontally and ahead of a face. In cross-section, they form an arch or roof, and that's what is the reason that is called pipe roof on arch. Here to the left, we can see what's essential concept of this pipe roof. Immediately after the excavation of a certain round, you can see that the ground is exposed, and the shotcrete is still fresh. And at that point, the pipe roof takes over some of this load, and it transfers it longitudinally. One part goes back to the part of the tunnel that is already supported, and the other part goes in front to the part of the pipe roof which is still in the ground. And by this, the result of this load transformation or transfer is that the displacements, the convergence of the tunnel is decreased, and also the stability conditions around the face are improved, and also within this region of the excavation, which is temporarily unsupported, the safety conditions for workers also improve. Now, as you can see, this is a problem that is essentially quite complex. We have interaction between primary lining between these elements, supporting elements and the ground, and this calls for 3D analysis. Now, in our case, we adopted the Plexis 3D software. Here is a list of some common features. So for obvious reasons, we adopted the longitudinal symmetry. The size of the tunnel in cross-section is typical two-lane tunnel with approximately 10-meter diameter. We used inclined pipes, which is normally used in practice. And this, because of this decision, we weren't able to use the conventional tunnel designer, which is installed in Plexis. Yeah? So we need to devise a different strategy. Moreover, we used beam elements for pipes. Initially, we started with embedded beam elements, but later I'll be commenting on this, our decision. Shotcrete lining was modeled with volume elements, and material model for shotcrete was concrete model, which meant that the time effect was also included to include the hardening of the concrete during the construction. The length of the round typically was 1 meter. We use a sequential excavation, as we can see, with top heading, bench, and invert. And temporary face support and temporary invert were modeled by surface loads. All conditions were drained and without presence of groundwater. And also the ground was modeled, in most cases anyway, with hardening soil model. Now, approximately 20 parameters of this model were varied during our parametric study. For each of these parameters, we analyzed how the variation of this parameter, one particular parameter, affects the output parameters. And these parameters were basically displacements of pipes, then internal forces of pipes, meaning axial forces, bending moments, shear forces. And moreover, we also, in some particular cross sections, we also analyzed what are the strains and stress states in the ground. Yeah? Now here are some of the geometric properties, and more also with material properties. Today I will be showing some results which regard mostly this one, this set of variations. Altogether, over 100 cases were modeled, and each case has approximately 250 faces, and which means that the process of input has to be automatic. Yeah? We devised a routine which generates approximately 4,000 instructions, yeah, for each case, and these instructions that then are transferred into command prompt of the Plaxis, and then it is executed automatically. So the human error is more or less diminished. And on the other side, also with the output analysis, we also did automatization to a large extent to simplify the process. Now to some results. Here we have some typical curves that we came across. So as you can see here, at the upper, so these are two cases for the stage when the face of the tunnel is approximately here at 20 meters, yeah? And you can see that vertical displacements here, in this case, this area is still underground, and here, of course, the deflections or the settlements are considerably lower, and on the other hand, the bending moments in this area, which is still embedded, are almost zero. Once we come to the face, then these settlements or vertical displacements start increasing, and here in this part, this part is already embedded in the previous arch. So here we have lower displacements. These waves that we have here are the consequence of the each stage that is excavated. So as we continue with excavation, each excavation adds another such wave to this bending moment distribution. Now, with regards to the variation of ground stiffness, in this particular case, we had two different cases. we have the blue line with more stiff soil or ground, 100 megapascals or with E50, yeah? And the red one with 50 megapascals, so much, approximately 2 times more flexible soil. And the result is such that if we have 50% decrease in modulus, this results in twice the settlements in the pipe, which is approximately expected. Yeah? On the other hand, with the bending moments, here you have some spikes, and the 50% decrease in the modulus result in approximately 20% of increase in bending moments. Now, if you pay attention to this shape, you can see that these two shapes are quite similar. Yeah? So what we did is we introduced a secondary axis, and one axis was for one case and the other one for the other one. And this is what we end up with. Yeah? So this is, on the left side, we have a scale for the 100 megapascal cases, and these cases are in this case, I think the solid lines. Solid lines. And on the other side, we have higher scale, because this one is for the 50 megapascal case. And as we can see, this one is, we've seen this one before in previous slide. Yeah? But now when it's scaled, it has an effect that it almost perfectly align one to another. And moreover, it also aligns in previous steps or phases. So when phase 13, this one, 13 meters, it's these two curves. So this shows that the behavior is, although with different parameters, but with some similarities. Yeah? Now, the next comparison is with variation of pipe stiffness. In this case, we use standard pipes with 114 millimeters and 140 millimeters. And 3 colors here in these charts designate different stations. So the blue one with station at 22 meters, the green one with 23 meters, and the red one with 24 meters. Personally, I have to say these results came to me as a bit of surprise, because I expected bigger difference, because the stiffer pipe should have an effect to cause lower displacements, but we can see that the effect is only minor for the displacements. However, on the other side, we have bending moments. Again, here the bending moments for the stiffer pipe are almost proportional to the higher stiffness of the moment of inertia. Yeah? Now, the third comparison is that we compare the variation of an initial stress state. Here, we compared the transverse and the longitudinal initial state with the variation of coefficient of thrust pressure, K naught X and K naught Y. And here in this picture, we can see 3 different sets. Yeah? And those 3 sets have in common this parameter K naught X. So these are vertical displacements, and we can see that the values, those curves that have the same value have also the similar vertical displacements. And, but to be more precise, the higher value of K naught X results in lower value of vertical displacements. Yeah? And to continue with the second comparison, here we can see a comparison of in cross-section. And here we can see that the change in initial stress results in considerable changes in direction of these vectors of displacement, and the higher values of initial state, initial stress, result in higher displacements in horizontal direction, both in transverse and longitudinal direction. And as I mentioned also earlier, that we have compared we have analyzed various actual case histories, and one most documented and well known in Slovenia is the case history of a pipe roof in Triana tunnel. This one was, in this case, the measurements were taken by horizontal displacement, and the analysis was very elaborate. And we took the results of laboratory testing from that time and ran the calculation, and we discovered quite good agreement with our with the actual measured displacements. This showed that our model can give very good comparison to actual states in the nature. Instead of conclusion, I just put some points for discussion. I mentioned earlier that we chose beam element instead of embedded beam. This is the reason why with embedded beam we got quite a funny results. This is the blue line for embedded beam, both for the axial forces and for the shear forces. They are these so shaped distributions which weren't realistic. So just to share our experience that in this case embedded beam element didn't prove very reliable. And another one also, we analyzed not only the crown pipe, but also those pipes that were on the other locations, and we can see here that the crown pipe has the highest bending moments here, yeah? And those bending moments decrease as we go to the outside of the pipe roof. On the other hand, the M3, so the bending moment that goes in the other direction, increases from top crown pipe to the pipe that is located on the edge, and this. As it turns out, that the values, the maximum values, still are of the same order, although the mechanism for the crown pipe is considerably different than the case in the pipe that is located in the edge. So thank you for your attention.
Hvala, Sebastjan.